Hello everyone. In this video, I'm going to talk about electron configuration of elements. When we are going to study this topic, I'm going to remind you in the quantum model, we are going to find the place of electrons in the atoms. So, for example, in the periodic table of elements, we know that for each element, how many electrons are available. For example, if we are going to study sodium, we may say that based on atomic number of sodium, we have 11 electrons for sodium. We are going to know how to distribute these 11 electrons for sodium atoms. So first, I'm going to remind you if we are going to work on the quantum model based on the Bohr's atomic model, we are able to have a number of shells for atoms. For example, shell number 1, shell number 2, shell number 3. So N represent shell number. And we are going to know how many electrons for each shell. For example, 2 electrons for shell number 1, 8 electrons shell number 2, and 18 electrons for shell number 3. We already talked about the number of electrons in each shell in other videos. So assume that I'm gonna work on sodium atom. I'm gonna write sodium. It has 11 electrons. So I'm gonna draw some shells for sodium atoms, and I'm gonna say that for shell number 1, we can add up to 2 electrons here. So 2 electrons for shell number 1. In shell number 2, we can add up to 8 electrons because shell number 2 can hold up to 8 electrons. So I'm going to write 8 electrons here. Totally, I just used 10 electrons for sodium atom, but sodium atom has 11 electrons. One more electron left, so I'm going to add the last electron here. So look here, I could distribute 11 electrons of sodium in these 3 shells. This one, it doesn't have any electron. There is no electron here. So it looks is redundant. So I'm going to erase that one. So it gives us this information. Sodium atom has 3 shells, and in these 3 shells we have this number of electrons distributed. 2 electrons for shell number 1, 8 electrons for shell number 2, and 1 electron for shell number 3. So by this method, we could distribute 11 electrons for sodium atoms. We are going to learn one method to distribute electrons for all elements or every single element in the periodic table. One thing, if you pay attention to this method, we just work on only shells. So I can say 2 electrons in first shell, 8 electrons on shell number 2, and so on. But I did not say anything about subshells. We learned that in quantum model, we have electrons can be addressed in shells, subshells, and orbitals. So we are going to work on this method. Whenever we have electron configuration of elements, so let me abbreviate by EC as electron configuration, we have different methods to report electron configuration. Using periodic table, using the periodic table, or without using the periodic table, without using the periodic table. And we have two types of electron configuration: abbreviated electron configuration and complete electron configuration. So in this video, I'm going to work on these two forms: abbreviated, complete electron configuration, either by using the periodic table or without using the periodic table. If we are going to work on complete electron configuration, so let me write the title of this section: complete electron configuration. This is one of the subjects you should work on, because most likely you have questions regarding this section in your exams. To do this, we need to have the Pascal tree. We need to know how to draw Pascal tree for this method. I'm gonna ask you to please pay attention. This is one of the easiest method to work on. When we are going to work on Pascal tree pattern, I'm gonna write 1 as a first shell, and we write the only subshell for this shell here, S. So I'm gonna write shell and its subshell. 1S, it means shell number 1 has one subshell, we call that S. In this other row, I'm gonna write the second shell number 2. In shell number 2, we have two subshells. Shell number 2, two subshells, S and P. I'm gonna write 2S, 2P. I'm gonna write all S's in one column. Shell number 3, we have three subshells, S, P, and D. And I'm gonna express that we need to write the shell numbers because we are going to know for shell number 3 we have three subshells. I'm sure you can easily write for shell number 4 we have four subshells, S, P, D, F. And gonna I'm going to continue for shell number 5. We have four subshells. If you already watched my video, you remember that we have only four subshells in the chemistry, S, P, D, and F. Shell number 6, S, P, D, and F. So we write like this one. Then I'm going to ask you to draw parallel lines to cross each shell or subshells. So I'm gonna cross that one. We call that 1S. So let me write it here, 1S. I'm gonna write parallel by this one, 2S. So it crossed 2S. I'm gonna write 2S. Same, I'm going to continue. Parallel by that, we cross 2P, then 3S. So 2P, then 3S. So let me write it here, 2P, 3S. Then I'm gonna continue with 3P, and we are going to cross 4S. 3P and 4S. 3P, 4S. Next one, I'm gonna continue here. We are going to cross 3D, 4P, and 5S. First 3D, 4P, 5S. And you can easily continue and write 4D, 5P, 6S. So, and you can continue to write 4D, 5P, 6S. What does that mean? We are going to fill out shells and subshells by this pattern, by this ordering. The reason, because electrons are negative particles. For higher shell numbers, subshells can be switched. So we have some exceptions. We cannot say after 3P we have 3D. Look here, after 3P, we should first fill out 4S, then 3D. So we have some changes in shells and subshells. For example, another change in this trend, after 4P, you assume that we have P subshells, we need to work on the D subshell. So we should say 4D. But as you see here, we need to first fill out 5S, then 4D. The reason for these changes, because in the elements with more electrons, we have more repulsion, and we need to find some explanation for the changes of the electron and writing by this order. Pascal tree pattern, it gives us this chance to work on this easily. Please understand, chemistry is a practical science. So whenever you are going to do some experiment, you can see in experimental point of view, you can verify this type of writing of electron configuration. So that is why it's 100% works, and we are going to apply by this one. So please understand, after for S, we don't have for P, we have 3D. So I'm gonna mark that one for you guys. We have 3D. Or if you are going to think about the another one, so you may say after this subshell 5p 5p, so you should have 5D, but as you see here we don't have 5D, we have 6s. And if you are going to work on the 6s, after 6s, so look here, if I gonna draw here, I'm going to fill out first 4f 5D 6p. So look here, after 6s we are going to have 4f. So these changes, or this in new type of fillet, the shells and subshells can be described by Pascal pattern or Pascal tree pattern. So I ask you, please learn how to write the Pascal pattern by yourself when you are going to work on electron configuration of elements. So let me erase this side one more time, and I ask you to have a practice for yourself and work on this. One more time, 1s, let me quickly write, 2s, 2p, 3s, not like me, 2p, 3s, 3p, 4s, and it's going to continue. Right now, assume that we have electron configuration of sodium, the example we already reviewed earlier. So I'm going to work on this example. So for this one, I'm gonna say 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 3d, 4p, and I will back, if necessary, I'm going to write the rest of the required shells and subshells. Right now, I'm gonna ask you, please remember that one. For S, P, D, and F. For S, we have 2 electrons, P 6, D 10, and F 14. And you already know how to memorize or how to remember them. Whenever you see S in this pattern, please add 2. So for S shells, sorry, S subshells or S orbitals, we add 2. For P, whenever you see P subshell, please add 6, and for D, please add 10. It means they are number of electrons. So I'm gonna look at the sodium atom and see how distribute these 11 electrons for this element. 2 electrons are here, 2 electrons are here, and 6 electrons are here. Totally 10 electrons. I need to have only 11 electrons. So if I have only 1 electron here, I could write 11 electrons for sodium. So let me cross that one, and I'm gonna write 1. So I cross that one. So all other shells and subshells here are redundant. So I'm going to erase them. So it's not necessary to keep them. So I need to have only 1 electron in this shell. I'm going to call that one 1s2, 2s2, 2p6, 3s1. What does that mean? It means we could distribute 11 electrons of sodium in shells and subshells. When we have like this, it says shell number 1 can have 2 electrons, and these 2 electrons are placed in S subshell. For shell number 2, In shell number 2, please look, shell number 2, we have 8 electrons. Let me highlight 8 electrons for you. These 2, and these 6. Totally 8 electrons for shell number 2. So I'm gonna write that one here. And for shell number 3, we can have up to 2 electrons. But here we have only 1 electron. And I'm gonna write it here. So this model, it gives you only shell distribution, but electron configuration, it gives you shell and subshell. So that is why we prefer to work on this model, working on electron configuration of elements. So this type of writing, we call that electron configuration of sodium. And we call that complete electron configuration because we wrote from A to Z, from the first shell to the last shell, from the first subshell to the highest shell number. Right now, I'm going to ask you to please work on another example. For example, I ask you to work on Fe26. So you may pause this video and look at the answer after that. Right now, I'm gonna erase this one and I'm gonna work by crossing here. 1s, 2s, 2p3s, 3p4s, 3d 4p5s, 3d 4p5s. And I'm gonna back and add 2 electrons for s's, 6 electrons for p subshell, and 10 electrons for d. S is going to be 2. And I need to count 26 electrons for Fe. How to get 26? Because atomic number of Fe is 26. It means 26 electrons for Fe. I'm going to count electrons. 2 and 2 and 6, totally 10 electrons here. 2, 6 and 2, totally 10 electrons here. It means we have 20 so far. And I need to have 6 electrons more. Here we have 10. I cross that one, I'm going to write 6. So 10 and 10 and 6, totally 26. So I cross here. So all other shells and subshells after that, they are redundant. So I'm going to keep that one as the final number of electrons. So as you see here, we could distribute 20 electrons for this element Fe. Right now, I'm going to work on abbreviated electron configuration. I'm going to work on abbreviated electron configuration of elements. So let me go to the next slide. When we need to have abbreviated electron configuration of elements, we just need to apply one specific rule. This rule, it says using the previous noble gas in the bracket, using the previous chemical symbol of noble gases in the bracket. What does that mean? Look at this slide. I'm going to work on sodium as one sample here. Sodium electron configuration, I'm going to write it here. The previous noble gas for sodium belongs to Ne. How to get that one? When we say noble gases, we are going to talk about the elements on the group number 8. So in this column, sodium, first let me talk about the noble gases. Helium has 2, Ne has 10, Ar, argon has 18, Ne krypton has 36, xenon has 54. So we are going to work on the radon 86 as well. So look here, previous noble gas of the sodium. Sodium has 10 11 electrons. So previous noble gas belongs to the element before that sodium. It means 10. Look, sodium has 11 electrons. So it's going to place here between 10 and 18. This is the sodium. Previous noble gas means 10. I'm going to write electron configuration of sodium by like this. In the bracket, I use the previous noble gas. I'm gonna use the previous noble gas chemical symbol Ne10. And right now, I'm going to start with the next or rest of the electron configuration. I'm gonna write 3s1. So what does that mean? It means I just placed all these electrons, all these electrons in the electron configuration of Ne, and we have only 3s1. How to get that? We need to keep 3s1 because always we start with s. Always we start with s. How to get that one? We should write 3 because always we need to look at the number of number of shells for each element. Shell, it would be same as the period number. Look here, period number 3 for sodium. So I'm gonna write the last shell is going to be shell number 3 for sodium. So I'm gonna write 3 and we add S1 here. I'm gonna work on the Fe26. Fe26. So look here, Fe is here. Fe is here. I'm gonna work on the Fe as a second example here. So let me keep that one here. Fe26. So please look here. 26 means we should have Fe here. The previous noble gas is 18. So I'm gonna write Ar. It means 18 electrons here. So right now I'm gonna know how to write the Fe here. Fe is period number 4. 1, 2, 3, 4. So I'm gonna write 4 and always we start with S. So Ar 18. So I have to add 2 electrons here. For S2 we have 20 electrons so far. So I need to work on the remaining 6 electrons. After 4s, we are going to add 3d. Please remember that one. After 4s, we are going to start with 3d. So we are going to have 3d. And the number of electrons for 3d because of Fe26 is 6 electrons. Ar18 and 2 20 electrons and 6 we have 26 electrons here. So this method we call that abbreviated electron configuration. Abbreviated electron configuration of elements. So let me write that one for you guys. Abbreviated electron configuration of elements. But right now I'm going to work on one easiest method. This method is applied when we can use the periodic table of elements. Easily we can get the electron configuration of element without knowing the Pascal pattern tree. Electron configuration of elements by using the periodic table. I'm going to ask you work on, for example, this one, potassium 19. We are going to know how to write electron configuration of this element by using the periodic table. Whenever we have the periodic table of elements, you may remember that we work on this classification. So we work on S block, we work on P block, we work on D block, and also F block. So they are going to be F block. When we say S block, please remember that period is going to represent the shell number. So this is the period number 1. It means this element has only one shell. Period number 2, it means elements are placed in period number 2, they have only 2 shells. Period number 3, it means elements in this period, they have only 3 shells. So we are going to work on this one, this information. Period number, it gives us shell number as well. So if we are going to know how many shells should be reported for each element, we need to know the period number. Potassium, we are going to check that one. So please look here, potassium period number 4. So we predict we have 4 shells for potassium. So let me draw like this one. 4 shells for sodium, for potassium. So this is the one thing you need to memorize that. Period number, it gives you the shell number. So I'm gonna work on the other information. On the first information, I'm gonna write 5, 6, 7. Please remember that in periodic table we have 7 periods. 7 periods. It means the maximum number of shells is 7. The maximum number of shells you can draw for each element is 7. So 7 is the maximum number of shells in the quantum model. Right now, I'm going to apply the rules. So always, if you have S block, you write S. If you are in the P block, you should write P. So if we have like this one, it means we are in the P block, only in the P block, and they are belongs to period number 2. So it means they are going to fill out 2P. If we are in the P block and they are in the period number 3, it means we have 3P. Please remember that always D subshell start at shell number 4 because this is the at shell number 3 because this is the third subshell. So S is the first subshell, P is the second one, and D is the third subshell. So whenever we start D, we need to write 3D. Always we start with 3D. So the first row that we have the D block, we call that 3D, and we continue like 4D, 5P, 6P. Sorry, 3D, 4D, 5D, 6D. And F, this is a fourth subshell. What does that mean? It means it should start with 4, 4F, 5F. So first subshell 1S. So the second subshell is 2. Always we start with 2 here on the right side, 2P. If we have D, 3. And if we have F, this is the fourth subshell, 4. So for sodium, we are going to reach out the sodium. So we are going to write like this one. The previous noble gas for potassium is AR 18. And I'm going to write for potassium. Potassium, it has this coordination. It has this coordinate. So I'm going to write 4, and it's going to be 1 electron here. So I'm going to write 4s1. So we write AR in the bracket for S1. If we have calcium, we should write AR 4s2. So this one, each column means 1, 2. And here we are going to have number of p electrons, p1, p2, p3, p4, p5, p6. Let me work on one example here, like nitrogen 7. Look at the nitrogen 7. We are going to talk about this element. The previous noble gas is He, 2. So I'm gonna write He, 2, and I'm gonna find nitrogen here. So I'm gonna say we start with 2. We need to pass these two elements. So 2 is 2 because 1 here and 2 here. And then we are in the 2p block. 2p block. We should say how many electrons here? 3. 2p3. So please look here, 3 and 2, 5, and helium has 2 electrons, totally 7. So right now, I'm going to ask you to work on another example to make sure you get this concept. So I'm going to ask you to work on, for example, Cl17. For Cl17 is here. So you are going to say that one, the previous noble gas, it means 10 Ne. So I'm gonna start for Cl from this side. So I start with 3, S1 is 2, and I'm gonna continue here 3p, and for the 3p block 1, 2, 3, 4, 5. So we write 3p5. And last thing I'm gonna work on, so you may work on the electron configuration of another example like transition metals. Like let me work on the Ni28. So I may ask you to work on this Ni28. So let's see how it works. Let's see how it works. So Ni28 is here. The previous noble gas is here. Look, 1836. So 28 is going to place here. So I'm gonna write AR in the bracket, and I'm going to start from this side. For S, we pass 2 electrons for S2, and we start with 3D. Please remember, we are in the 3D, and we just need to count 1, 2, 3, 4, 5, 6, 7, 8. So we end to 3D8. So this is the electron configuration of AR for S2 3D8 for Ni28. So then back to this slide. So period number represents shell number. For potassium, we have 4 shells, so that is why we could draw like this one. And if you remember that, you can easily apply this method to write electron configuration of elements. One more thing, if we have, for example, K19 AR4S1, this is the last shell. It's represented by the period number. We call this one valence shell. Valence shell. Valence shell is the highest shell number. Highest shell number. Highest shell number. This is the last shell available for your atom. Highest shell number. Right now, I'm going to talk about these electrons. This electron is placed in the valence shell. This electron, we call that valence electrons. So valence electrons are electrons placed in the valence shell. So number of valence electron for potassium atom is 1. It has only one valence electron. Look at this example, Cl17 in E 3s2 3p5. So if I ask you what is the valence shell for this element, the highest shell number here, so valence shell is 3, and the number of electrons in this valence shell 2 and 5, totally 7 electrons. So we say valence electrons are 7. Right now I'm gonna give it you one information to get easier this concept. I'm gonna say that group number it gives you the number of valence electrons. Group number, it gives you the number of valence electrons. So this is the another information you may need to know. For example, look at the potassium. Potassium group 1, we have only one valence electron for potassium. So you don't need to draw to find this information. Chlorine, group number 7, we have 7 valence electrons for chlorine. So let me back to this slide. So I'm gonna erase, let me erase quickly this information to ask you some question to work on. So assume that we are going to work on this question. Number of valence electrons and valence shell for each element. What is the valence shell and valence electron for each element? Valence shell means group number, valence shell means period number, and valence electrons means shell number. So let me ask you, how about magnesium? Magnesium. Look at the magnesium. 1, 2, 3. Period number 3. So valence shell is 3. And number of valence electrons, group number 2. 1, 2. Group number 2, it means magnesium has 2 valence electrons. Let me ask you another example regarding sulfur atoms. So sulfur is here. So we are going to say sulfur period number 3. We have valence shell is shell number 3, and the number of electrons for sulfur. Sulfur group number 6. It means we have 6 valence electrons for sulfur. If you draw electron configuration of sulfur, you end to Ne 3s2 3p4. So please look here, Ne 3s2 P1, P2, P3, and P4. So it gives you 6 valence electrons for sulfur atoms. We need to work on valence electrons for the next chapters. So other electrons are reported here in Ne. We call them inner electrons. And we don't work on inner electrons of elements. Only we focus on valence electrons. We don't work on the transition metal of elements in the periodic table to ask you about the number of valence electrons or valence shell. We prefer to focus on mostly main elements. Hope this video helped you to understand how to work with the number of electrons in each atom, how to distribute them, and how to identify S, P, D, and F block with using the periodic table. Thank you for watching this video.